Hey everyone. So in this video, we're going to be kind of getting an introduction to our newest unit, Unit 5, on momentum and impulse. And so before we dive in and start looking at kind of what the heck I've drawn already here, I really just want to talk about some of the things that we've really gone through. We just finished a unit on energy. And energy is not a vector, it doesn't have a little hat over it, and it's this quantity, it's this thing that objects can have, right? Whether it's something up in the air, or it's something rolling around the ground, or it's something that's compressed against a spring, and there's other many types we haven't even looked at in this class. But energy is this quantity or thing that objects have. And similarly, momentum is another quantity or something that objects have. Now, in the case of energy, there were all these different kinds of energy. We had kinetic energy, that was 1/2 mv squared, where m is the mass, v is the speed that something's going with. We had this gravitational potential energy, which was just the mass times g times how high up the thing was. And you kind of got to choose where that value was 0. Then we also had kind of spring energy, which was 1/2 the spring constant times how much that spring is compressed or extended squared. And so we had all these different kinds of shapes for energy. Here's one shape, and here's another shape, and here's another shape. Now, momentum is a lot simpler in that there aren't different forms that it really takes. Momentum is something that can be conserved, just like energy. But really, it's just the product of its mass and velocity. And so momentum is a vector because we have velocity, which is a vector right here. It has a direction and it has a size. And then we have mass, which doesn't have a direction, which is really nice. That would make life really complicated. And since we're multiplying this thing that is a scalar that doesn't have a direction by something that does have a direction, we end up having momentum p, which has a direction. So let's say you're walking 5 meters per second south. That's your velocity. You have a mass of, let's just make an easy number, 100 kilograms. Well, your momentum is equal to your mass times your velocity. You're going to get 5,000, right? And now we get kilogram meters per second, and that has a direction. So we have to include south. So really easy. It's just multiply m, multiply v, you got it. Now, I kind of have here two different little blobs, two different little masses. One's smaller, it has a smaller mass, object 2. Object 1 is much bigger, it has a bigger mass. Now, the neat thing here is both of these can have the same momentum p. They can have the same momentum, but only if the object that has a bigger mass has a smaller velocity. Or in other words, as long as object 2, the smaller one, has a greater velocity in the same direction. So the neat thing here is really that these are directly proportional. This kinetic energy equation that we dealt with last unit was kind of tricky because if you double the speed, you quadruple the energy because that v is squared, but the mass isn't squared, and so they kind of had different impacts on it. In this one, if you double m, you're going to double the momentum. If you double v, you're going to double the momentum, which makes things a lot simpler and more straightforward. So that's it. That's all there is. That's one of our equations on the AP equation sheet, and this is one of them. The other equation, or concept really, is impulse. And we'll dig into a little more, kind of the connection you see maybe at the bottom here. Impulse is the product, that means multiply, the product of a force and the time t that it acts. So what the heck does that mean? This is kind of weird. If I had a graph that had force as my y and t as my x value, so we're kind of looking in graphs now, but we'll kind of write it this way. Impulse equals force times the change in time. We'll just write it like that for the moment. So if I go and I take force and I multiply it by how long, I will get this thing now called impulse. If we were to graph it then, well, if you do the force times the time, that's finding the area of this graph. That's kind of finding all this green space here. And so we could have made it an easier graph and just said, oh, it's a constant force over so long. You find the area of the rectangle, and that is the impulse. This is kind of a neat relationship that you could be given a force and a time graph. And if you took the area of it, you would immediately be able to find what the impulse is. Now, I have another silly example here. I have this gray cat, Bagheera, and so I've gone and I've drawn him here, and he loves boxes. I get a box and I unpack it and open it up, and he just like hops right on in. But sometimes he goes and like lays against the box, and the box shifts a little bit, or he bumps up against it. So let's say Bagheera acts with a force of 3 newtons. Let's say he's acting for 3 newtons and it goes to the right from here over to here. So it travels some distance and it takes 2 seconds. Well, I know a force, I know the time. I could just plug directly into this and go, oh, well, his 3 newtons multiplied by the time would give me, well, 3 times 2, that's 6 newtons times seconds. Or we can kind of rewrite it and unpack newtons and go, well, a newton is equal to a kilogram over a meter per, or sorry, kilogram meter over second squared, and then we're multiplying by seconds, and so this little one right here goes away. So we could write it either of these unit-wise ways. Oftentimes, this is the more common way. But that's it. We could find the impulse, okay? Now, last unit, if we wanted to find the work, not the impulse, we would have said, oh, well, work is now force times distance, not time, it's distance. Well, we knew the 3 Newton force, that's what we plug in here, but we don't know the distance. So it's a very similar thing. It actually is just that easy, but you got to know just how to use it. All right. Now, we got the gist on momentum. We got the gist on impulse. Let's just connect the two. Why are these two related? Why are we even talking about them? They seem very, very differently related things. One is mass times velocity. One is force times time. What the heck's going on? Now, here's the cool thing. The neat thing is that an impulse, so what we just kind of looked at here, is the only thing that can change the momentum of an object or a system. So impulses will change the momentum. And this actually is looking at what we did a couple units ago in a different way. So here's the way that I like to connect the two, or the way that I would say it. I would say that a system, whatever the heck you're choosing to focus on, a system's momentum will change when an external, that means outside, impulse is delivered to it. So in math language now, a change in momentum is due to an impulse. So essentially we've gone and we've taken these two equations and connected them together. We said that changing this is equal to this. That's really it. That's all I've done here. We've just taken these two and kind of slammed them together. And so what that means is we can kind of start playing around and connecting things now. So I want to mention, though, that choosing a system is really important here. You can choose a system where momentum does change, or you could choose a system where that momentum might not change. And I will show an example in just a second here. So actually, let me show the example right now. Let's say that you're pushing against someone. You're like playing this silly game where you're trying to push each other over, okay? And in the beginning, you both are just standing still at rest, but you're kind of pushing against each other, all right? But in the moment, you're pushing against each other, you're acting with a force, but your momentum, your mass times your speed of both of you, if the system is both of you, is 0. So we have 0 momentum. The combined amount of U2 is not moving to the left, it's not moving right, so this velocity thing is 0, so the whole momentum is 0, right? Now, let's say that you actually shove against them or they shove against you, and one of you is bigger than the other, as I've kind of portrayed here. Well, it's true. They're going to go flying one way, and maybe you're going to go flying the other way, right? Now, here's the thing, though. You pushing against each other That's like an internal force. Like that's within the system of you two, right? That's not something that's outside acting on you two combined. You're pushing against them, but they're pushing against you. This is an internal force. So what that means is that you're going to be moving to the left. You will have, let's say, some negative momentum for you. So I'm going to call you object one. Your friend is going to have a positive momentum. They're going to be object two, right? Combined, though, this momentum was zero in the beginning, and combined, since there was no external force, just an internal force, there's still zero momentum. So how the heck can one of you have a positive momentum and one of you have a negative, but the total is zero? Well, it means that these two are equal in size. This one is just as big as this one. And so if this one's -4, this one must be +4. Those cancel out and become zero. And I did just make up numbers there. So the weird thing about it is since we looked at the system as both of you combined, there's zero momentum in the beginning. So there must be zero momentum after because there's no external forces. There's no forces outside. Now, if we chose to look at just your friend here, they would have zero momentum still in the beginning. So P is still zero. Their momentum after, though, would not be zero. We would have to change this actually. So in the case where it's just them we're looking at, kind of right here, well, we said they're moving to the right. So now we're going to have some positive value, some positive number. We don't know what the number is. Maybe it's 4 again, right? But now we're going, well, now the momentum isn't the same. If the system is both of you combined, the momentum is zero before and after. If the system is just them, it goes from zero to a positive value. Why is that? Well, now you are outside the system. You applied an external force on them, and that changed their momentum. So what the heck does that mean? It means that if this force is outside the system, the momentum will change. If there are no external forces, well, this change in momentum here is going to be zero. That's what it really means. And so for an isolated system, so where there are no external forces, no external impulse, momentum is conserved. And this is an always. This is a big one in physics. That's actually an always, which is kind of cool. So there's no change in the momentum within the system. Now, I've already kind of hinted at this a little bit, but we use P for momentum before, but momentum after is this weird thing where there's this little apostrophe up here. We call this P prime. That's how you would actually say that. So we say, oh, the momentum before equals the momentum after, or P equals P prime. And I will admit these both should have the little hats on them, little vector arrows, because momentum has a direction. So the momentum before equals the momentum after. And what I would like to do is actually show you where this first equation even comes from. So you don't just have these equations to memorize, you have them on your equation sheet, which you should have now. But the idea is that if change in momentum is the force multiplied by the time, we could go ahead, we could plug in Newton's second law here, F equals ma. We could plug that in for force. And so then we could rewrite it as the change in momentum is now equal to m times a times delta t. But acceleration is the change in velocity over the change in time. It's how much you're speeding up every second or slowing down, right? And so we can then plug that in for a. And so now it's gotten really gnarly looking, but we have our delta p, our change in momentum, is equal to the mass times the change in velocity over the change in time times the change in time. So the times cancel, and we get that the change in momentum is equal to m times the change in velocity. Now, let's say you're on the highway, though, you're driving down 101 or something, you're on cruise control, you're like, my speed isn't changing, my velocity isn't changing, I'm going 60 miles per hour south. Well, this delta then doesn't really mean anything. There's no change. There's zero change. So you can absolutely drop the little deltas here and here, and you just go, oh, well, what's my momentum? Well, my momentum is equal to my mass times my velocity, which does have that direction part to it. And so what I'm hoping you've kind of gotten out of this, one, these equations all kind of come from each other, as a lot of things do. But the more important thing is that we can connect this big equation to this equation. Since both of those on the left side are delta P, that means we can set this right side, this right side equal to this right side. And that will be really handy and convenient sometimes, being able to kind of recognize when it's appropriate to do that. So I hope that makes sense. Please write down questions, comments, concerns, anything that doesn't make sense. So when I do see you, you can ask those. And otherwise, thanks for watching.